Greetings, mathematicians. So today we're going to take a quick look at second derivatives of parametric equations. And so if we recall, previously in class, we took a look at the first derivative. And the first derivative, dy dx, is a function of t. So if we take the second derivative of y with respect to x, we are taking the derivative of a function of t. And so we need to think about utilizing the chain rule. And so this right here, this is the derivative of a function with respect to time. So if I'm going to take the derivative of that, then I need to take the derivative of the outer function, and that would give us the second derivative, okay, with respect to time, okay? And our variable that we are differentiating here, t, also needs to be differentiated with respect to time. We need to apply the chain rule here, and so we need to multiply by dt dx because we are taking the derivative of the t variable with respect to x. Now, this statement here is the same as if we had f double prime of t divided by dx dt. Dividing by dx dt is the same thing as multiplying by dt dx. And so we are taking this derivative of the derivative with respect to time. So that is our, if we look at Leibniz notation here, that is the derivative with respect to t of dy dx. Okay, and that was a function of time itself divided by dx dt. All right, so that's kind of the general conceptual framework. Let's actually apply this to a particular scenario. All right, so let's look at scenario number 1 here. So suppose, for example, we were going to find the second derivative of the following parametric equation. So let's say we had x of t is e to the t and y of t is t e to the t. So let me go ahead and in red here, I'm going to find dx dt. And dx dt, well, the derivative of e to the t is itself, so that would be e to the t. And then dy dt, I'll do that in blue here, dy dt, I need to apply the product rule because I have the product of two different functions. So the product of t is 1 multiplied by the second function, plus now we keep the first function t, times the derivative of e to the negative t. That requires a chain rule. Its derivative is going to be negative e to the negative t. Okay, so it's the derivative of e to the negative t there. Okay, now, because we're going to use this, I'm going to simplify a little bit. And so dy dt is e to the negative t minus t e to the negative t. Okay, so now, if I am looking for the first derivative, dy dx, that is the derivative of y with respect to time, divided by the derivative of x with respect to time. So I am going to take our dx dt, which is in red, and I'm going to take our dy dt, which is in blue, and I'm going to take the dy dt divided by the dx dt. So let's go ahead and do that. So dy dt is e to the negative t minus t e to the negative t divided by, now the derivative of x with respect to time is e to the t. Now, because I'm going to be utilizing this to find the second derivative, I'm going to do a little bit of simplification because otherwise I would be forced to use the quotient rule, which fractions inside of fractions, I don't know about you, but they get ugly pretty quickly. And so I'm going to try to avoid that. So let's do a little bit of algebraic simplification. So this becomes e to the negative t minus t e to the negative t times, now that denominator, e to the t divided by e to the t, is the same thing as taking e to the negative t. Okay, so let's go ahead and I'm going to distribute the e to the negative t to both of those terms. And so what I get for the first term, e to the negative t times another e to the negative t is e to the negative 2t minus t e to the negative t times e to the negative t, once again, is e to the negative 2t. So this is going to be the most usable, so this is our dy dx, our most usable dy dx. Okay, so that's our first derivative. Now, if I want to find our second derivative, let me scroll up just a little bit so I have some space here. Our second derivative with respect to x is the derivative of dy dx with respect to time. So I'm going to take the derivative of my dy dx, but with respect to time. And then we said previously we have to take that and we need to divide that by dx dt, because we have a chain rule here, because dy dx is dependent upon time. So let's go ahead and I am going to take, so in orange, I have our dy dx. So our dy dx is this guy right up here. So that's going to be e to the negative 2t minus t e to the negative 2t. And my dx dt is what we got earlier up here, which is just e to the t. And so let's go ahead and plug in e to the t, and that will be our second derivative. Now, just like in the land of non-parametric equations, when the second derivative is negative, our function is going to be concave down. When the second derivative is positive, our concavity is going to be concave up. And that's true whether we're dealing with parametric or non-parametrics. So that is our first example. Come on back a little bit later and we will take a look at another example utilizing the second derivative. So I'll see you around.